Good morning everybody. Last time we had started with the chemical equilibrium and we have seen in the introduction of chapter the spontaneity of the reaction can be determined with the help of the thermodynamic parameter, that is the delta G, change in free energy, and we have seen that when this delta G is negative, therefore the reaction is spontaneous. When it is positive, the reaction is non-spontaneous. So we see the different types of the equations related to the free energy. We had seen the change in a free energy, standard free energy, this type of the equation for the reactions we have seen. Now let's go to the chemical equilibrium. What the chemical equilibrium is exactly? The chemical equilibrium, see, some reactions, generally some reactions goes to the completion. That means the reactants are quantitatively converted into the products, and the amount of the reactant which is left unreacted is very negligible. That means that in such type of the reactions, the reactants are practically completely converted into the products. A very negligible amount is left behind. Such reactions are said to go to the completion. But many of such reactions are there which does not go to the completion, or where they stop at some situation or at certain time during the reaction. For such reactions, let's take one example. The example of dimerization of nitrogen dioxide. This is the reaction where nitrogen dioxide is brown in color, while this is colorless. The product formed is a colorless. Now in this reaction, if we take an evacuated vessel, and in that vessel if we take this gas, nitrogen dioxide, which is dark brown in a color, as the reaction goes, the product will be formed which is a colorless. Therefore, it is observed that the intensity of the dark brown color decreases as the reaction goes. But even after a long period, the vessel does not become exactly colorless. What does this mean? This means that some of the nitrogen dioxide is remain in the vessel which is not reacted at all. We will observe that the color of that evacuated vessel, some of the brown color, fade brown color, is constant after some time. What this shows? This shows that the reaction has stopped and all the nitrogen dioxide we have taken in the vessel is not converted into the product, and that's why the brown color of that evacuated vessel is a constant. And this shows that all the nitrogen dioxide is not converted into the product. This means that the reaction is not going to the completion. But actually, it seems that, or it appears that the reaction has stopped. But it is not the case. Actually, some activity is going on at the molecular level. Some activity in the sense, actually, here the conversion of the product, the conversion of the reactant into product is going on, but at the same time the product is also again converted into the reactant. So at this situation, the reactants are converted into product and again the product are converted into the reactant. Therefore, there is no change in the concentration of the reactant as well as the product. And this situation in the reaction is called as the chemical equilibrium, or equilibrium itself it is called as. At the chemical equilibrium, or when the equilibrium is established in the reaction, the rate of the forward reaction and rate of the backward reaction becomes equal. And therefore, after the equilibrium establishment, there is no change in the concentration of the reactant as well as in the concentration of the formed product, and this situation is called as the formation of the chemical equilibrium in the reaction. It appears that after some time there is no change in the concentration, but actually some activity is still going on. The amount of the reactant converted into product is equal to the amount of the product again converted back into the reactant. So reaction is going on. It is not stopped actually, but the concentration of the reactant and the product remains the same or remains constant. Rather than same, we must say constant. The concentration of the reactant and the product remains constant. This situation in the reaction is called as the chemical equilibrium, and at this condition the reaction seems to be stopped because no extra or there is no increase in the concentration of the product. Let's see another example. The formation of carbon dioxide and hydrogen from steam and carbon monoxide gas. This is the reaction. For this reaction, if we take carbon monoxide and the steam of water in an equal concentration, and if the reaction goes, therefore, this is what is actually the graph which is showing the change in the concentration of the reactant and the product. Obviously, this curve is for the change in the concentration of the reactant, while this curve is for the change in the concentration of the products. The same amount or the same concentration of both is taken. They are reacting in 1:1 ratio. 1:1 ratio in the sense one molecule react with the one, and therefore there is a formation of one of the molecule of this and one molecule of this. Therefore, the change in concentration of the reactant is shown by this, and the change in concentration of the product is shown by this. As we have taken equal concentration of both of this, therefore we will observe that at any time of the reaction, the concentration of this left unreacted will be same, as well as the concentration of these two products will exactly be same at any condition of the reaction. Now here, as the graph shows, what this line is showing? This line is showing equilibrium. What does this mean? The graph has become flat on both for the reactant as well as the product. This shows that the reaction has stopped. That means there is no change in the concentration of the reactant and the product. That means the concentration of carbon monoxide and the water vapor and the concentration of carbon dioxide and the hydrogen, their concentration will not change further, and this is called as the equilibrium. The chemical equilibrium is formed in the reaction. This type of the equilibrium, chemical equilibrium, as some activity is going on at the molecular level. That means the forward and the backward reaction both are going on, but they are at the same rate, and therefore the concentration of reactant as well as the product remains constant. Therefore, these type of equilibrium are not static, they are dynamic. Dynamic in the sense activity is going on, but the concentrations are remaining constant. This is called as the dynamic equilibrium. So here, at any condition before this equilibrium, we will observe that the concentration of both of reactants will equal, and the concentration of these will also be same. Their concentrations will be same, but eventually a time comes where the concentration of the reactant and the product becomes constant. That is called as the chemical equilibrium. Now we are more interested, or it is very important to note that, or to know that how far the reaction goes, to how much extent the reaction goes, where the equilibrium is exactly established. That is important to know. So therefore, where the reaction actually, to what extent it goes, thermodynamically it is steady. That thermodynamics tells you how much extent the reaction has gone. The reaction goes, or reaction proceeds till the Gibbs free energy of the reaction is minimum. This is the important condition. Whenever the reaction proceeds to how much extent or how far long it extends, it exceeds or it proceeds till the Gibbs free energy of the reaction is minimum. Now the next we will go to, that is the law of mass action we are going to see. Now what is the law of mass action? Now the law of mass action is the rate of any chemical reaction is directly proportional to the concentration of the reactants raised to their proper powers. See, for example, this is the reaction. Therefore, the rate of this chemical reaction is directly proportional to the concentration of the reactants raised to their proper powers, raised to the proper powers in the sense the coefficients of the reactant molecules which are actively involved in the reaction. So this is the law of mass action. The rate of any chemical reaction at any instant is directly proportional to the concentration of the reactants raised to their proper powers at that instant. This is what is the law of mass action. Now actually this law of mass action is not at all used. It is of the only historic interest. But to decide the rate of reaction, this law of mass action was used. This is K, a small k. This is a proportionality constant which is also called as a rate constant. And I have told you that this is now not used. It is only of historic interest. A new law is formed and that is used. That is law of chemical equilibrium. Law of chemical equilibrium. Now what this law of chemical equilibrium is? This law of chemical equilibrium is that the ratio of the product concentration raised to their proper by the product of reactant concentration raised to their proper power is constant at equilibrium. This is what is the law. Let's understand what this law is. Let's again consider that simple reaction. This reaction we have considered. Now what this law of chemical equilibrium is. Now here we have seen that at a chemical equilibrium, or when the equilibrium is established in the reaction, the rate of forward reaction, that means this reaction, and the rate of backward reaction are equal. Let's first write the equations for forward and backward reaction. See, therefore, the rate of forward reaction. Now, according to the law of mass action, this will directly proportional to concentration of A raised to A, concentration of B raised to small b. And therefore, we can write this as Rf in small. This is equal to Kf. Now, this is a rate constant for the forward reaction, hence F, forward reaction, into concentration of A raised to A into concentration of B raised to B. The rate of backward reaction, according to the law of mass action, this will be proportional to C raised to C and D raised to D. Therefore, RB, backward reaction, the rate of backward reaction, is equal to KB. This is the proportionality constant or say rate constant for the backward reaction. So these are the rate equations for the forward reaction and the backward reaction. Now we have seen that at chemical equilibrium, both of this rate becomes equal. Hence we can write . equilibrium, Rf is equal to Rb. Therefore, Kf into concentration of raised to A raised to A, B raised to B is equal to Kb. Kb into concentration of C raised to C into concentration of D raised to D. Now actually what I am doing is Kf divided by Kb is equal to, I am taking this on this side, this on this side. So C raised to C, D raised to D divided by capital A raised to A and B raised to B. Therefore, this, the rate constant for forward reaction divided by the rate constant for the backward reaction. This is termed to be a new constant which is called as equilibrium constant, which is equal to C raised to C, D raised to D divided by A raised to A, B raised to B, where Kc is equal to Kf divided by Kb. So this is what is the equation of law of equilibrium, where Kc is called as the equilibrium constant, and that equilibrium constant is equal to the product of the product concentration raised to their proper power divided by the product of reactant concentration raised to their proper powers. Kc, the equilibrium constant. Actually here